out waves on vorticity discontinuities. So I think this connects. I mean, it's really interesting for me to hear all the sort of related stuff, which I was not so much aware of. But I want to say this is no water waves. There are no water waves here. This is pure vorticity dynamics in 2D Euler. So, but I still think it connects a lot with some of the things we've heard. So first, my collaborators. This really goes back to stuff I did in around 2010 with Joseph Biello, who's a colleague of mine at Davis. Then some of the work is with some graduate students. Ryan Marino Vasquez is a graduate student at Davis. Jingyang Xu was a former PhD student of mine. Very unfortunately, he sort of decided to leave academia after a postdoc. So he's now an analyst at Morgan Stanley in London. And then Xingtian Zhang, who was a postdoc of mine who's now at West Virginia University. And so the problem I want to discuss, so this is sort of I want to look at a special class of solutions, 2D incompressible Euler. And the unperturbed problem is just this shear flow. So you have constant vorticity in two half spaces on either side of a vorticity discontinuity. So I guess I'll use alpha shear rate. So alpha plus is shear rate above the discontinuity, alpha minus shear rate below. If nothing else, shear rate is good because I go crazy trying to think of whether I should use omega for vorticity or frequency. So it's the worst part of this whole subject. Okay, so here's sort of a picture of this is the unperturbed shear flow here. You have two linear shear flows. This is the symmetric case here, but in general, you can have zero or non-zero or different shear rates above and below. And then the vorticity discontinuity is just sitting here at y equals 0. And then it gets perturbed, and then you have some perturbation to the velocity field as a result of the discontinuity moving. And we're sort of assuming everything decays exponentially away from the discontinuity to the shear flow. And it turns out, well, first of all, this is linearly stable, this problem, unlike the vortex sheet problem where you have, jump in the tangential discontinuity, tangential velocity. And you have waves that propagate along the interface. These waves are unidirectional. The problem's not is not reflectionally invariant in X. If you rotate, you not only change the direction, but you switch the alpha plus and alpha minus. And the waves only go in one direction. So it's purely a unidirectional problem. I think with the larger alpha on the left, or in other words, the larger vorticity on the right, if hopefully that's correct. All right, so we can start maybe with the stream function vorticity formulations. I'm sure probably everyone here is familiar with this. You introduce in 2D Euler, you introduce a stream function psi. The velocity is some perpendicular gradient of the psi, and then the vorticity is basically this grad perp is just the minus dy dx. So you have two scalars here, the stream function psi, the minus the vorticity alpha, and then alpha satisfies this advection equation and with a velocity u, and then the u is reconstructed non-locally from the psi. So this is sort of the classic active scalar transport equation. You have a scalar alpha being translated, but with velocity u, and then the u is reconstructed from the alpha by solving this Laplace equation. Now, since you have a transport equation, it's compatible with piecewise constant weak solutions. So you can look at solutions where like the ones I did, alpha plus remaining alpha plus above the discontinuity, alpha remaining alpha minus below the discontinuity. All right, so now maybe the most familiar example of this is the vortex patch problem, where you have some bounded, simply connected region omega of t, where the vorticity is, let's say, 1. Inside that region, it's 0 outside. And then going back to Zabusky, you can write down contour dynamics equations, basically given the location of the vortex patch, you can reconstruct the velocity field. Then you apply Green's theorem, that's Biot-Savart law essentially. Then you move the boundary of the patch with that velocity, and you get a closed set of equations for how the boundary moves around. And that's the idea of contour dynamics introduced by Zabusky. And then actually back when I was sort of just time I just described when I was finishing my PhD, that was a very actively studied problem. I mean, it's still very actively studied, but Maida raised it as a question of, you know, does the boundary of a vortex patch become singular in finite time? And that was sort of a model problem for, well, the singularity issues people are actively looking at today and making a lot of progress. And there was, you know, contradictory numerical evidence. Chemin in 1991 actually proved it remains globally smooth in time. But it's no surprise the numerics was sort of hard to give a definitive answer, because this is some numerics by Dritschel using contour dynamics for an elliptical vortex patch. They throw off these extraordinarily thin filaments. It's sort of, I don't know, doubly exponential in time blow up in the curvature probably. And, you know, this is one of Dritschel's remarkable computations, you know, showing how this is an unstable elliptical patch. It throws off these guys and then they just wind around the patch. And well, it's looks very singular, but it's globally smooth, the boundary. So my interest is in looking at this in kind of simpler geometry, namely half-spaced geometry instead of patches, you know, where you have the geometry of the ellipses or whatever is more complicated. So I want to look, essentially, you can think of this as a planar version of a vortex patch. So just a boundary here. And I'm going to assume the discontinuity as a graph rather than try and do the full parametric equations. I mean, you can do the full parametric equations as well, but I mean, it's kind of like, I think of it like water waves. Okay, we understand a lot by looking at KdV or something. Okay, if you want to know about breaking of water waves, that's a more complicated problem. But before this filamentation occurs, I think there's still a lot to be learned from looking at these simplified equations where you just have one unknown displacement to think about this displacement. I'm not sure phi was a good letter to use for this, but that's what we end up using. So the phi is just the displacement of the free surface. All right. So as I said, these discontinuities are linearly stable. Rayleigh, in fact, looked at this problem in 1895, I think, first, as part of his, you know, program of shear wave, stability of shear waves and shear waves in Euler. And he found, he did both a linearized stability actually in a channel, and then he also looked at the nonlinear stability, and I'll make a comment about that in a little bit. Now, the thing I want to say is, and of course, he found everything was stable. At least, I mean, not asymptotically stable, but at the linearized level. Now, this problem, once you put it in a half space, there's only two parameters, the alpha plus and alpha minus, which are both frequencies. And we've sort of seen this in some of the other talks too. So the result of that is that if you look at the dispersion relation, the frequency of the waves don't depend on the wave number k. Right? So they just have this basic frequency omega 0, which is the jump in the vorticity over 2. However, they're incompressible, they're unidirectional waves. Frequency has to be an odd function of k. So you get this dispersion relation, omega of k is omega 0 signum k. Okay, for the one unidirectional wave. Okay, this signum k is basically the Hilbert transform. So that Hilbert transform comes in. And now, so I'll write some. Oh, and here's what I want to emphasize. So these waves are non-dispersive. In fact, they have zero group velocity. They're just basically oscillating up and down at each point. The derivative of the group velocity is 0. Okay, provided we're away from k equals 0, so that's kind of the long-range stuff, which is, you know, somewhat singular in these, you know, putting everything in a half space. So you have to worry about what happens there. But what I want to emphasize is they're very different from non-dispersive hyperbolic waves, which have constant wave speed. And we'll see how that works in just a minute. All right, so now what I want to do is show you some contour dynamics equations for these half spaces. Now the problem is, of course, if you look at a vortex patch, the vorticity is compactly supported. You can just write down standard Biot-Savart integrals and get the motion of the patches. These half spaces, now you have to deal with unbounded vorticity distributions, and that causes issues. The naive Biot-Savart integrals don't converge. So what you want to do is sort of somehow truncate, apply contour dynamics, and send things off to infinity. But to do that, you need absolutely convergent integrals. Otherwise, it's going to depend on how you truncate things. So one way to handle this is we look at the general velocity as the sort of unperturbed shear flow plus a perturbation. And the vorticity of this perturbation is confined to some strip in Y, some finite strip. So the picture looks something like this, for example. This is one way to do it. Here's the unperturbed interface. This might be the perturbed interface. So out here, the vorticity is, alpha plus. Down here, it's alpha minus. And then here in these regions, the vorticity perturbation is alpha plus minus alpha minus. And here it's, alpha minus minus alpha plus. So under some suitable assumptions on the phi, it has to go to 0 infinity. And the derivative has to go to 0 faster than 1 over x to the alpha, 1 plus alpha, to get convergent integrals. So then you can basically, what you can do is you can truncate in x, write down the Biot-Savart law, you get absolutely convergent integrals, and you just send the x cutoff to infinity, and you end up with some contour dynamics equations for the phi. And they look like this after you do some manipulation. So here I'm non-dimensionalizing this omega 0 to 1, and then this m is this ratio of alpha plus plus alpha minus over alpha plus minus alpha minus. In the symmetric case, that m would be 0, for example. But in the case where you have maybe non-zero on one side and 0 on the other, it will be non-zero. And sort of you extract the linear terms, and you end up with this equation here for the motion of the front, okay? So this is, okay, phi derivative. There's a Burger's type term here, d by dx of half m phi squared, depending on this parameter m. And then this is sort of the contour integral term. This is basically a cubic term here, because the log expands to a phi squared. As I said, so long as you have the decay of phi x that I mentioned, all these integrals converge perfectly well, both at the sort of singular point and at the zeta equals 0, and also at infinity. And the h here is the Hilbert transform, which we've seen many times already. So it's convolution with principal value 1 over pi x, or on the Fourier side, it's with my sign conventions, it's multiplication by minus I signum k on the Fourier side. So let me first say a word about the linearized equation. All right, so the linearized equation is phi t is Hilbert transform of phi. And what the solution looks like is, it looks like f of x cos t plus Hilbert transform of f sine t. So these solutions just oscillate. It's some profile f of x, which oscillates up and down in time. And it oscillates from f to Hilbert transform of f to minus f to minus Hilbert transform and back again. It's kind of like half of a simple harmonic oscillator. And the dynamics of this is the front is basically behaving like a collection of simple harmonic oscillators, but they are coupled through the fact that their velocity is the spatial Hilbert transform of their displacement. That's kind of the unidirectional, what the unidirectional part does. Again, if you compare with non-dispersive hyperbolic waves, there you have at the linear level, you have a wave which just translates. Here you have a wave which just oscillates up and down with frequency 1. You switch on nonlinear effects, and what happens is the nonlinear effects are going to modulate that spatially varying profile. Now, the key thing here in terms of nonlinearity is, what are the dominant resonant nonlinear effects? Well, there are no three-wave resonances in this problem. All right, because if you have 3 wave numbers adding up to 0, the frequencies can't add up to 0. All right. So this differs a little bit from the talk that Mark Blythe gave. He also had sort of constant frequency modes in his problem, but there was also a 0 frequency mode. And so his 0 frequency mode could interact with 2 non-zero frequency modes. But here it's just the pure non-zero frequency modes, and there are no So unlike the Berger's type non-dispersive hyperbolic case, there's no three-wave resonances, no quadratic effects. Okay. On the other hand, when you go to cubic effects, you have a whole slew of four-wave resonances, because any four positive wave numbers that add up to zero, the frequencies will also automatically add up to zero. So in some respects, it's a bit like what happens in the non-dispersive hyperbolic framework, where you have a whole lot of resonances, but instead of those being quadratic three-wave resonances, you have this whole slew of cubic four-wave resonances. And it's also different from dispersive waves because there you're limited by the dispersion relation about what resonances can occur. So it's kind of, I find it a very interesting, different type of non-dispersive wave motion. And we'll see the dynamics is also quite different. So let me mention, going back to Rayleigh for a second. So Rayleigh, as I mentioned, did a nonlinear stability analysis of the vortex sheet. He computed the response of a fifth order, up to fifth order in the wave amplitude for a sinusoidal dispersion, sinusoidal disturbance of the interface, and didn't find anything particularly interesting. I think he sort of lost interest in the problem after that, or at least he didn't do any more work on it. But the point I want to make is this, that if you think about what it takes to get the energy cascade started in this four-wave resonance, if you just start with one wave number, you never generate any new wave numbers. It's basically K is K plus K minus K. And so Rayleigh didn't see any interesting nonlinear dynamics. He was essentially computing the Fourier expansion of a periodic traveling wave moving along the front. But once you have two wave numbers, then the whole thing kicks off. You have 1 and 2, and then you can generate 2 plus 2 minus 1 is 3, and so on. But you need two wave numbers to get started. So, so this is, and just to, so Rayleigh didn't see that because he just started with one wave number in his sinusoidal equation. All right, so let's do some weakly nonlinear asymptotics. So here's the solution. We'll look at solutions of size epsilon. This is the linear part taken out, the oscillating profile. And then we have, instead of the F, we have some profile, which I'm calling V, depending on X. So the V of X is the profile that's oscillating up and down, and then it's getting modulated on 1 over epsilon squared timescales, because as I said, the nonlinearity is four-wave cubic type nonlinearity is going on. And you get the following asymptotic equation for how the profile evolves. So it's a cubic equation. You can see you have these non-local terms in here. Mod dx is just multiplication by mod k on the Fourier side, so it's basically Hilbert transform x derivative. And I should say, not in this form. Dritschel sort of derived some equations related to this. I believe they're equivalent, although I could never quite correlate his notation with my notation. But he derived them by taking the circular vortex patch and then sort of writing down equations for weakly nonlinear disturbances of a circular vortex patch, and then basically sending the vortex patch to a plane. That was how he derived it. It has a small thing that then the vorticity is always going to be 0 on one side of the discontinuity when you do that, since he was starting from a vortex patch. Then with Joseph Bielo, my colleague, we derived this equation written in various forms directly from Euler. So rather than using quantum dynamics, we just did an expansion of Euler, get the equation there. Since then, been interested in various aspects of this. Now, so I'll explain this more as we go along, but so one can actually prove that this equation does give you an asymptotic approximation for the contour dynamics equations that I wrote down before. So that's a rigorous proof that the formal asymptotics actually does indeed match the full contour dynamics equation. It's not complete. That's not a really straightforward argument, although it's sort of understood now ways to do it, because you're basically doing sort of normal form methods for quasi-linear equations, right? And the main obstacle is in the original contour dynamics equations, you have this quadratic term here in general. And the nonlinearity is really operating, the resonant nonlinearity is operating on the cubic timescale. So this has to be removed by some sort of normal form near identity transformation to get the cubic approximation on the right cubic timescale. So one can do that. All right, what I want to show you is this. All right, I switched from V to U, but this is the equation again, normalized coefficients, the asymptotic equation. And again, you start with two initial wave numbers. As I said, you have to do that to kick the dynamics off. And here's a numerical solution by pseudo-spectral method. Now, what's happening here? So this is basically showing you the evolution. This is like a sort of Poincare mapped profile every 2 pi. This is showing you how that profile evolves. And at some time it breaks down. And if you do full contour dynamics, Joseph Bielo did some very rough contour. They're nothing like Dritschel's contour dynamics, but anyway. But this wave that suddenly appears here, everything is nice up to this point. This is when the wave starts to filament. The boundary is starting to filament. If you do the contour dynamics, you see it's starting to throw off filaments. And it's throwing off filaments every 2 pi units of the underlying rapid oscillation. And so and I think in this limit, there's sort of infinitely many filaments. I mean, the number of filaments being thrown off is going to infinity as the epsilon goes to 0. So you can imagine the underlying picture of the discontinuity is really complicated. Now, it's pure speculation. We know everything is good up to that singularity formation. It's okay. I admit it's pure speculation about what's going on after that. But I believe these filaments are so incredibly thin. They're not, it's kind of like almost doing contour surgery by asymptotics. I don't believe the filaments are really affecting the global behavior of the discontinuity. I find this, behavior kind of fascinating, that the weak solutions of the asymptotic equation, I believe, are continuing to make some predictions after the graph description breaks down. So it doesn't seem like solutions of the asymptotic equation, they seem to remain continuous. You don't see discontinuities forming in the asymptotic solutions. Now, in a slightly different direction, I want to comment. So we call this the Burgers-Hilbert equation. So it's basically a Burgers equation with a lower order Hilbert transform. And it's what you get from the contour dynamics equation by throwing away all the sort of non-local cubic terms. So it looks like a very simple equation. You have Burgers plus this Hilbert transform thought. Now, kind of the remarkable thing is, if you normalize the coefficients in this Burgers equation correctly, the cubic asymptotics for this guy is exactly the same as the cubic asymptotics for the full contour dynamics equation. So this gives you a very good picture of the nonlinear dynamics of these vorticity discontinuities. So that's in a regime where the solutions are small slope. So what's happening at the linear level, the Hilbert transform is driving this profile that's just oscillating up and down. Then you add Burgers steepening on top of that. So in sort of one phase of the oscillation, the wave tries to steepen a little bit, then the oscillation comes back down and the wave expands. And so you have this successive compression, expansion, compression, expansion. And that's what averages out, normally for burgers, you would expect, 1 over epsilon breakdown of solutions. But because of that averaging effect, you get the 1 over epsilon squared smooth solutions. Smooth solutions persist for times 1 over epsilon squared. And this small amplitude regime for Burgers Hilbert is very different from what you normally think of as happening in burgers. Now you might ask, why does such a simple equation work like that? Well, there are actually some dimensional considerations which show you that this Burgers nonlinearity is the right quadratic nonlinearity to put in. So all these equations are Hamiltonian. I haven't talked about the Hamiltonian structure much. They're Hamiltonian with respect to the sort of Gardner type operator d by dx, which is what they inherit from the full Euler Hamiltonian structure. And if you look at, you can learn quite a lot about just looking at dimensional analysis in Hamiltonian problems. And the key thing here is these are surface waves. They're codimension 1 surface waves, meaning that the wave number is 1 dimension less than the density that sets the mass scale. So in the plane, you have a density per unit area, and the waves are unidirectional. And the only dimensional parameters are frequencies. And you can show that this is exactly the kind of nonlinear term that respects that scaling. It's not the most general one, but you have this very simple local term that does that. So that's some explanation of why this Burgers Hilbert equation is relevant to the Vorticity discontinuity. All right, so I already said some of this, that you have linear oscillations in time that get alternately compressed and expanded by nonlinear steepening expansion. As a result, you get, for initial data whose slope is of order epsilon, you get smooth solutions on times 1 over epsilon squared instead of the usual 1 over epsilon just for burgers. And you can prove that by, again, by normal form methods. And roughly what's going on is when you use a normal form method, you eliminate this quadratic nonlinearity, you get exactly the cubic terms in the asymptotic equation that I wrote down before. You remove this non-resonant term, and then you get the cubic resonant terms in the asymptotic equation showed previously. So here is a numerics for that Burgers equation. This is for a relatively large value of epsilon. So you can see it looks very similar. Again, there's not as many oscillations given the finite value of epsilon, but you can see the overall behavior looks a lot like the asymptotic equation. And in this case, this is like a Wiener scheme, shock capturing scheme. So this case, what happens when these things are forming is that's the shocks forming in the Burgers Hilbert equation. And if you look in detail at that shock formation, this maybe will go by very fast, but you can see these tiny, tiny shocks. You see this very characteristic sort of little peak forming. And somewhere in there, there's a shock forming, a tiny shock. The contour dynamic simulations look very similar to this prior to filamentation. So what happens is the shocks form, the back comes down and the shock gets hit by a massive expansion wave. It absorbs the expansion wave and it becomes extraordinarily weak. Now, I don't have a proof, but I think there's good reason to believe that once the shock forms, it never actually completely disappears. So you have this background thing, you have shocks forming every period, and you then are getting solutions with more and more shocks. Those would sort of correspond, I believe, to cutting off the filaments and just replacing them by a shock. It seems like that, again, that's pure speculation, but what I believe is happening. Okay, so I'm going to finish up just in a minute. Let me just show one other thing, which is sort of separate from this discussion. One can also look at generalizations of the stream function vorticity equation. So here, instead of having minus Laplacian psi equals vorticity, we have some fractional Laplacian. And alpha equals 2 would be Euler. The other important case is alpha equals 1. That's the surface quasi-geostrophic SQG equation. What's interesting about that is, and then you can look at sort of discontinuities and solutions of SQG. Now, one thing that makes SQG interesting is if you look at SQG when alpha is 1, you see that theta is not a frequency anymore like the vorticity, it's a velocity. So I think it's one reason why SQG is relevant to fluids, because in SQG you have a velocity being transported by a non-locally constructed velocity. Now, one thing I thought when I did this, well, okay, dimensionally, there's only velocity parameters here, so we must get non-dispersive hyperbolic waves. And that was kind of my interest in looking at SQG. But that turns out not to be the case, because the sort of unperturbed shear flow for SQG is actually a logarithmic profile. Basically because Hilbert transform of a step function is a logarithm. So that logarithm sort of spoils the scaling invariance, right? If you rescale y, you actually rescale the velocity by a constant factor. The usual thing like dimensionally, you can't have log y, you have to have log y over some parameter of the same dimension. So it turns out this problem is not sort of hyperbolic scale invariant. It actually has a scaling Galilean invariance. You rescale and you do a Galilean transformation, and that's the invariance. And this was observed by Pfefferman and Rodrigo in some work they did. But so here's what I just want to show you what the contour dynamics equation looks like. And you see the linear term is actually a log mod dx vx. So you get this strange logarithmic dispersion coming in. And then this is the cubic nonlinearity here. Now, I thought maybe this would behave almost like non-dispersive waves, but that's not the case. I mean, it seems like this logarithmic dispersion is still strong enough to make it behave like a standard dispersive wave, t to the -1/2 decay. And in fact, I proved with Jing Yang and Qing Tian, we proved if you start with sufficiently small, smooth initial data, you actually have global smooth solutions. So no filamentation occurs. The dispersive decay is strong enough to stop filamentation for small. The large slopes is a different story, of course, but you do get global small smooth solutions. But mostly I just wanted to, I don't know, point out this interesting, I haven't seen this sort of logarithmic dispersion show up in any other places. All right, thank you very much for attention. I'll stop.